Welcome all to this session in which we are going to study dependent motion. But before we start, I would like to inform you that section 12.9 is going to be divided into two parts. So this is part number 1. The objectives of this part is to define the dependent motion for you, to teach you how to establish a proper datum, and to teach you how to write the chord equation, or sometimes it's called the effective length or even the equation of the cable. In many kinematics problems, the motion of one object will depend on the motion of another object. So, as an example, if we look here, the motion of the boat over here, will definitely depend on the motion of the person, because they are connected by a cable. Same here, the motion of this box will depend on the motion of the motor here, and so on. Now let's start establishing the kinematics of dependent motion. So in this figure, we can see that we have two blocks, block A and block B, and they are both sliding into different inclines, as you see here, but they are both connected by a cable or a rod. Now, what is important over here is that to establish the kinematic relation, we will start by length. And if you look carefully over here, what we are going to do, we are going to establish a datum. This datum, as we all know, datum are usually established on a fixed point. So if you have this point, which is fixed, it's at a pulley fixed to this structure, then we can establish the datum to this block. We call the position of this block B, SP, and we can call the position of this block SA. Now we have indeed three lengths over here. The length A to C, the length C to D, which is marked with red, and the length D to B. So it is assumed that no matter how A and B move, the length in contact with the pulley is constant. That's the pulley. It's always constant. And for that, we can write the equation as follows. So we can say that SA plus the length of the segment CD in contact with the pulley, the red segment, plus SB is equal to the length of AB, which is constant. Now, if you look over here, so this is the red segment. So what we are saying basically that this length plus this one is always constant. This means that this cable doesn't stretch. It's always the same. Now, if we differentiate that cord or cable equation with respect to time, we are going to get dSA over dt plus d length CD over dt plus dsp over dt, which is equal to the dl from A to B over dt. Now, clearly here, this term is equals to 0. And this one is also equals to 0. And the reason why is that this length will never change. Even if a block A moved all the way to here, and block B moved all the way to here. Yes, the length SP and the length SA will change. This one will get longer, and this one will get shorter. That's going to be SP, and this is going to be the new SA. but the length of CD is always the same, and the total length is always the same. So what we can do, we can say that what we are gonna get VA equals to minus VB. Now let's look at this relation. Now if we look at this relation, we can see that VA is equals to minus VB. So let's look at this carefully. Now if you see that length A is getting longer while length B is getting shorter, and why the minus sign is there is that because VA is moving in the direction of the datum. The datum was established like this. This is the positive sign. So VA is indeed positive, while VB is actually negative. So, which means that one of them will move opposite to the datum, to its datum, and the other one will move toward its datum. Now, if the motion is reversed and VB, block B ended up moving in this direction, and block A moved in that direction, this sign will also adjust. We'll discuss this more further. So, but you should know that there are many possible ways of defining a datum. So, but what you should keep in mind is that the definition of the datum is always the same. It has to be defined at a fixed position. In many problems, there are possibilities that you will get multiple lengths like CD, which is this one. So instead of calling them different names, you can just assume that they are added to the total length. So if this is the same equation that we wrote previously, we can just write it like this. We can say that SA plus SB equals to L, which is constant. So there is no need to add LCD or any other constant length, because they are simply going to vanish when you derive them with respect to time. That's it. In this slide and the next one, we are going to have this example where we are going to write down the kinematic relation, the velocity, the acceleration. We will write down the chord equation or the cable equation, but we are going to do this with different datum. So this is just to teach you how you can set up different datums, but you still get the same answers. So let's see how are we going to do this. So for this one, as you see, we set up two different datums. So one here, fixed one for A. So as A moves to the right, it's considered to be positive. If A moves to the left, it's considered to be negative. And as we see here, we marked the red little segment over here with on the pulley, so it is fixed. Also, we marked this segment, and this segment also with red, because they simply don't change. They are always the same. And here we have this green segment, and it is measured with the length here called H, which is the distance from block A to the datum or this pulley. Now, this part, which is not marked over here, I may just try to mark it with a blue, this one and this one. This one is, of course, going to change as the motion changes, so as the motion is set, because when a block B moves down, this pulley will move down as well, so this length will get longer and longer, because the pulley will be moving here or there, so as you see. And what we did, we said that from this datum, so datum is also established at a fixed point, so this point is always fixed because the pulley here is fixed to the wall. Then we can say that downward for B is positive and upward is negative. So if you want to write down the kinematic relations, then we start with the length. So we say S A plus H plus 2SP is equals to L, which is constant. That's it. Now we differentiate with time, and what we are going to get? We are going to get 2VB equals to minus VA. And we are going to get 2AB equals to minus AA. Now, what does this tells us is the following. It says that when object or when block B moves downward, which is positive, A will move to the left, which is negative. And this is shown up here in the equation. Now, if you move A toward the positive side, it means that you are going to substitute a positive value over here. And then you will have a positive multiplied by a negative, which means that the velocity of A as a direction is going to be negative, which makes sense. Because if A moves to this side, we all can see that B will move upward. And upward is negative to the direction of the datum, the positive direction, which is downward. Now, let's move on to the next slide and see how we can get this differently with a different datum. So here, again, we have the same problem, but this time, instead of defining the datum at different location, like before, we are actually going to establish the datum at the same point for both block A and block B. So this is the datum of SA. Again, right-hand side is positive, left-hand side is negative. And for block B, what we did, we measured the length all the way to the pulley. Now, the pulley itself represents the displacement of block B because this distance is always the same. So when the pulley moves 1 centimeter, for example, this means you will have the block B moving 1 centimeter. So here H is constant, but the idea is that we are going to use H in order to define the length of these two segments. Now, again, we represented the length, which doesn't change on the pulleys over here with red. And if we want to write down the equation for the code, then we'll have SA plus H plus 2 multiplied by H minus SP, which is equal to L, which is equals to constant. Now, if you look carefully over here, we just want to add the different segments of the code. So basically, this is one segment. This is another one. This is two segments. That's the length that we are calculating. And if you look carefully, this can be measured as SA. This can be measured as H, while these two segments can be measured by this part or calculated by this part, which is 2H minus SP. What are we doing here? We're saying that we are going to have all of H minus SP, and what is going to left is this. But this length, we have it twice because we have two cables, and this is why I multiplied by 2. Again, H is constant, L is constant, so if we differentiate with time, we're gonna get 2VB equals to VA, and 2AB equals to AA. Now, definitely this is not the same equation that we get in the previous slide. So let's discuss the differences in the next one. So let me write down the equations. On the right hand side, we had just expressed the relation as 2VB equals to VA and 2AB equals to AA. On the left hand side, we had 2VB equals to minus VA and 2AB equals to minus AA. Now, let's start the discussion. Very simple. If you look at this, if block A moved in the positive direction, so if a block A moved here, that's A, then what's going to happen to block B? It's going to move upward. So block B is going to move upward. And of course, the bully is going to move here, and these two lengths will get shorter. But what happened is that block B just moved upward in the direction of the positive direction of the datum, and block A also moved to the right, which is also in the positive direction of the datum. So this equation is actually perfect. The same goes with the acceleration. Now, again, I don't want to run the scenario just to save the time, but if block A move to the left, it's going to be negative, and block B will move downward, so also negative, because they are opposite to the positive direction of the datum. That's it. If you look at the left-hand side, what we have over here, if a block A move to the right, then it is positive. And this is why you will put a positive number over here, and you get it multiplied by a negative, so you get negative, which means that the velocity of A is going to be some constant number, but it has a negative sign. And the reason is that as A move to this direction, B will move up. That's what we said even here. We said if this one moved to this direction, this one will move up. So same here. If this one moves to this direction, this will move up. And if it moves up, then basically that's B. This means it is opposite to this arrow. While this one is the same as this one, which means that one of them would have the negative direction compared to the other. So you can run the same scenario. If, for example, if block B moved downward, which is positive, so you apply a positive number over here, but block B will move to the left-hand side. Left-hand side means the velocity of A has to be negative. And if you substitute a positive number in here, and you solve for VA, this negative will go there, and you will get a negative number, which is perfect. So both equations give the same result. Now we are going to just set up a procedure for analyzing a dependent motion. But what you should know here is an important note is that these procedures can be used to relate the dependent motion of particles moving along rectilinear paths. As you saw before, the blocks, the bullies, everything was moving in a rectilinear, just straight lines. Only the magnitudes of velocities and acceleration changes. So the magnitude of the velocity and acceleration, not their line of action, which means that they move, their magnitude changes along that straight line, whether left or right, but there is no rotation, no other thing. There is no curvilinear motion, in another word. So how do we set up the problem? First, you need to define the position coordinates from fixed datum line along the path of each particle, and this is what we did. Different datum line can be used for each particle, like for block A and block B. Then relate the position coordinate to the chord length, and this is the chord equation. And then just identify the segment that doesn't change and just ignore them. You don't need to put them in the equation and then say that the derivative with time is equals to 0. The third step, of course, is to write down the chord equation, but you need to be careful that in some situation you have two chords. And if you have two chords, it means you have to write two chord equation. And what matters here is that you will need to have a parameter, one single parameter that relates the two chords together. And then you differentiate the position coordinate equation with time to get the velocities, and then you have to differentiate it again to get the acceleration. So this is the end of part 1. We will continue this section on part number 2.